Hey everybody, and welcome back to Algebra 2 Online. So today is the day where we're actually going to finally get into these inverse root functions. So square roots, cube roots, those kind of things. And really we needed to talk about inverses a lot in general because particularly like the one thing this slide is getting at, which is the kind of finicky thing with this idea of being an inverse versus a well-defined inverse. So just to start off, I just want to kind of get you thinking about this a little bit. So do some odd degree polynomials have a well-defined inverse, i.e. like pass the horizontal line test? And yes, definitely. If you take x cubed, right, that looks like this, and definitely that passes the horizontal line test. You could even have x to the, 35th, right? And basically that one, it kind of comes in, it's a little flatter, but it's still a curve, and then it's flat again, and it keeps going. That one's still going to pass the horizontal line test. Like, it's not horizontal there. If you zoom in and zoom in, it really will be a curve that's kind of always going up and up and up a little bit. So those, yes, definitely they can happen. But what about an even degree polynomial? Do some of those have a well-defined inverse? And the answer to this is no. Even the simplest one, like x squared or something, right? Certainly fails, right? That fails. You draw a horizontal line there and you hit two spots, right? Other graphs too, like if you did, something like that, some sort of x to the fourth thing, again, hit more than 1 point, so it fails the horizontal line test. So no, none of those would. And so, basically what we've done in math is we wanted to have the capability of using inverse functions for these to some level of success. It's not perfect, okay? So that's why I say fix in quotes, but there is going to be a way that we can kind of fix in quotes the cases where the inverse is not well defined for these even root functions. And so basically this is what the inverse should look like. If you take y equals x squared and you did the whole thing whether you flip it over the line y equals x, you would literally, y equals x. This graph would truly flip to that. And so this blue one is what it should be, okay? But the reason we have to fix stuff is that the inverse, if it was the blue graph, would fail, the vertical line test all over the place here. That is an issue, and we don't want our, things that we're programming into a computer to not be functions and whatnot. We want to have a very nice behavior with the inverses. And so what we actually have to do is we have to figure out a way to delete part of this graph. And the weird thing is that we actually could have deleted the bottom, or we actually could have deleted the top. It's very possible that, like, the way the world worked out with math is that we could have had this curve be defined as the square root of x, which is then the inverse to this x squared. And we would have had things like this, where we would have done, okay, square root of 9 is just a -3. It's very possible that's the way it could have gone. Now it's, really we had choice, and we just decided that it'd be weird if we got negative numbers out of the square root. And so we just thought, like, human beings are going to like the positive numbers. And so when we were designing math thousands of years ago, we basically just took that to be the graph, and we deleted this. And the way that we do it is actually using another operation in math. And so what we did is we basically said square root of 9 is not -3. We defined square root of 9, to be 3. Basically, we want it to be positive, and we don't want negatives. And the thing in math that would take any negatives and make them positive and like pop it up here is the absolute value function. So what we actually have for square root of x squared, if you ever are doing this, the correct way to actually write the answer is absolute value of x, not x, okay? Square root of x squared does not equal x, because if square root of x squared equaled x, then you would get the weird not function kind of thing. So this absolute value is super important, and I think I said it in a previous video, but this is the kind of thing that even my calculus students can struggle with. We run into square root of x squared and stuff like that all the time, and they sometimes forget that they need this absolute value. This has actually got a name in math. This is called the principal root, but it's not super important. But it's the principal one because it's the positive one, and it's kind of thought of it to be the actual value of this kind of thing. Whereas there is this other thing going on with negative x down here, but we're just taking the positive one. And we take the positive one by just slapping absolute value on it. So anytime you see square root of x squared, do not put x. It will be wrong. Okay, it's gotta be you gotta put absolute value on it. Otherwise, you're going to run into this, right? If you do, if I use that example again, square root of negative 3 squared, then you could think of as negative 3. And you can get exactly what we said we don't want, which is the numbers down here. So we chop that stuff off. We never, ever, ever let the output of the square root be negative. And so we can do that by just sticking these absolute value bars on it. Super important. So just to kind of show you one more time, this is really what it looks like, okay? We can do, I really wanted to get it perfect. So 3, and that should be negative 3 over there. If you do both those in the square root, x squared, right? We know we square them and we get, I went too high. Right there, and right there. And we know that both of those are 9, right? Negative 3 squared and 3 squared is 9. But if you go into literally Desmos or something, you type in square root of x, okay? You're only going to see this curve that just goes on and on forever. And then if you plug in 9, okay, you just go back to right here, which is 3. So it's a weird inverse because it's doing something like this. It's like saying you had 3 and negative 3, and f takes that to both of those to 9, right? But the inverse only takes 9 back to 3. Does not take it back to negative 3. You're losing some information with that inverse relation there. But the benefit is that it's a function. That's the idea. You lose stuff, but we get that it's a function, which in our math makes things easier. So that's what's going on. And this is probably one of the most misunderstood things. Like a lot of times students don't really get why the even roots need this fix to happen. Really a simple answer. All it is just in order to maintain its behavior as a function. If that part's there, you don't have to take the absolute value thing. You're going to allow for positives and negatives, and then you're going to get something that's not a function. All right. So on to very important inverse functions. So we've just studied a bunch of these, right? We studied these polynomial functions. They could keep going, right? We could do like x to the 5th and 6th and x to the nth, right? There are inverses for some of these, and some work better than others. Even ones not going to work as well as odd ones, okay? If you do, if you ever do like a square root of x squared, or a 4th root of x to the 4th, or a 6th root of x to the 6th, any of those even ones, you need to fix it with the absolute value thing, okay? The odd ones, totally good, okay? You do not need to fix it, right? So even ones will always equal, here, let's just do red for evens here. So we'll do it like this. So it'll equal absolute value of x if it's even, all right? And so this one is even, and then we'll do one over here that's odd. But then if it's odd, cube root of x cubed is truly just x. The nth root of x to the n is just x if n is odd, for even n and odd n, we'll say. So just be careful of that and you'll be okay. If you put x for this one and x for this one, it will be wrong. You're going to get points off. It's going to mess up answers. So that's the most missed thing in this unit. I guarantee you right there. Just try not to forget. I wanted to show you how these things are working because this is really important actually too. So we need that when we compose the functions, the square root and the x squared, they need to give us, x. Now, we know that also we're going to need absolute value, but we need x to the first power. That's the important part. And this square root is operating on x squared. And actually, the weird thing that maybe not everyone knows is square root is really a power. It's really raising x squared to something so that the exponents work out to the first power. And if you just remember like middle school properties of exponent stuff, x squared raised to the 1/2, right, is how we would get this to be to the first, because it would be 2 times a half, and then it'd be x to the first. And same kind of thing applies down here. If we want the cube root of x cubed to cancel out, then basically we need to raise x cubed to the 1/3, right? And so then you could do 3 times a third and really get x to the first right there. Same thing for x to the 4th root of x to the 4th. We basically just go and raise x to the 4th to the 1/4, and then 4 times the 4th is 1, right? There's like a 1 in there. And so that's literally what you do no matter what the root is. You can have like a 83rd root, and it's just 83, sorry. It always just follows that same pattern. So if I wanted to do the nth root of x to the n, it's raising x to the n to the 1 over n power, and it is again equal to two different things. It's either equal to x for odd n, or it's equal to absolute value of x for even n, okay? So this is actually, these root functions are arguably my least favorite thing in math. I never understood why we went through the trouble of inventing a new symbol when we have perfectly good symbols for fractions already. This is really all you should think of as root functions. Now, you also have to know that when you see these, that's what these are. So sadly, these are symbols in the world that the math world has made you also learn. But they really are just fractional powers. They're just, you see this little symbol. That's the only one that's actually not written. We imply a 2 there, but you should never write the 2 because it's the smallest one. You're not going to take the first root. That doesn't really make a lot of sense. So yeah, you see these kind of roots, just think fractions. Always 1 over whatever the thing is, the number there is, okay? And they do have some special names just for the first few, which you should know really already, right? This is your square root. Then you get cube root. And pretty much after that, they just go by the number. So we say 4th root, and then like so on and so on, 5th root, 6th root, 7th root. Then we could call this the nth root. So you'll never really hear me call these other ones something special. They're just 4th root or 5th root or whatever. All right, so with that in mind, we can finally talk about stuff like this. So this is a perfectly okay thing in math. basically what you want to do is you want to look at powers as two different kinds of functions. This is really like a composition of functions right here. You have a power function, polynomial kind of thing, and then you have like a 1/5 in there, which is going to be like a root function. So you can think of this as, so I'm going to do the 2 in blue, let's say, and the 5 in green. So I can think of this actually two ways. I can either think of it as x squared and then raised to the 1/5, or the 5th root of x squared. That is one way to think of it. All right. Or I can think of it as the trying to keep all my colors correct here. So the 5th root. So like that. Well, we don't need the parentheses there. Let's just do the 5th root, and then all of that stuff squared. Okay. So again, the only other option there, I guess, is that. I messed up my colors. OCD is tough. Okay. So you can think of this thing in one of two ways. You can either just think of it as x squared and then a 5th root, or you can think of the 5th root first and then x squared. And that's just because powers are commutative, right? Or multiplication is commutative. So when you do a power of a power, you can just swap this order. It doesn't really matter which way you do it. So that is a perfectly okay thing. Typically, what you're going to see me do is, I think everyone would agree that this right here is the simplest way to write any of these, right? There's no reason I should split them up like this, or no reason I should add that silly symbol. So pretty much that's all I ever write. I just write, the 17/3 power of x, or the, 4/3 power, whatever. So that is pretty much how you'll see me do it. Down here, I just wanted to do a few examples where I kind of show you how I could simplify these roots, basically. So let's do that. So we get a 6th root of x to the 18th, which I want you to think of as x to the 18 divided by 6, right? Because it's like the 1/6 power. And then we know that 18 divided by 6 is 3. And probably the most common answer I would get from students would be that. But if you thought that was the right answer, you'd be wrong because of what I just talked about over here a bunch. You are doing an even root of a, x to the 18th in here. So you cannot let this thing equal a negative. If you do, then you're allowing this thing to happen, where you're allowing a graph to be created that is not a function. And at times that's okay. There's times where circles pop up in math and whatnot. But we want, for most purposes, we want our math to work out very nicely. And so we want a well-defined function, not just a graph. A graph is something that's not a function. So we want an actual function. So the way we do that, pop absolute value on it. And then you'll be fine. That is the correct answer to that. Okay. For this one, we're not going to need to worry about absolute value because it's odd. You don't need to do that, right? So here, I'm just going to literally do, I'll just do this in a few steps. I'm going to raise this whole thing to a 5th, right? That's what the 5th root is. And then negative 32 is going to get raised to the 5th. A to the 15 over 5 is what we'll get there. And then b to the 10 over 5, right? So we kind of have one of these properties of exponents where you can kind of distribute that 5th in. And then you can just go all these simplified pretty nice. This is negative 2, this is 3, and this is 2, right? And you don't need to worry about absolute value. Odd root, no need to do it, okay? Only even roots do you need to worry about absolute value. So I just got a few more. I think these are the last ones I want to do, examples. and just more kind of simplifying problems. This one's always kind of funny because it looks kind of scary with like 72nd root in there and stuff. But if you look at it a little more carefully, you've got the 72nd root of the same thing, right? So basically think of this as like negative x plus 2x. That's literally how I see it, which would be equal to x, right? But x is the 72nd root. So you really just have one 72nd root of x left over, which again, if you want to write it this way, that is perfectly okay also. But that is really as simple as you could go with that one. So for this one, this uses, so in order to simplify this, you can see I've got like the same base in here. We know that like if we have, we have the same root, right? So we know that if we have something like square root of 2 times square root of 3, we can combine it into one square root and just multiply and get 6, right? I'm basically going to use that to get started. So I'm going to combine my cube roots, and I have x plus 5 squared times then x plus 5 to the 4th, which is 6 of these x plus 5s, right? And then if you cube root x plus 5 to the 6, it's like doing 6/3 there. And 6 divided by 3 is 2. So this has the exact same value as x plus 5 quantity squared. That is what that thing would equal. And you can't go any simpler than that. I mean, you could double distribute it out, but that's not simpler. This is simpler. So that is that one. And then this last one, kind of similar start. So the same way that you can combine, when they're multiplied like this, you can combine it into one big cube root. You can do the same trick, right, if they're divided. So I would probably start by just doing a cube root of that big thing divided. And then, there's some nice stuff that happens here. You have x over x, that's going to cancel. Y over y to the 7th, so that's like a 6, right? And then you're going to have cube root of 27 y to the 6 left over. And so now I would probably apply my fractional power. Do 27 to the 3rd and y to the 6 over 3. And so we get 27 to the 3rd is 3, right? The cube root of 27 is 3. And then 6 divided by 3 is 2. So 3y squared. So that one simplifies all the way down to actually 3y squared, which is nice. So this is the kind of thing that you're going to have on the homework, some of this kind of stuff, just kind of getting you used to using, simplifying with like even and odd root functions. And by far, the most commonly missed mistake I see is this one. Please, please, please be careful about that. If you take an even root, you have to make sure that your answer has absolute value. Otherwise, you're going to have this issue right here. We don't want this part here. So take absolute value, pop it up, make it all positive. It'll look like that, right? Now you do lose info, right? We can't go from 9 back to -3, but this is at least a function, which is more important. It's like, it's the best we can do.